Welcome back, everybody, to the deep dive. Today we're diving into something pretty crucial, the world of long context language models.
Yeah.
These things are really the backbone of some of the biggest AI leaps we've seen lately.
Yeah.
The kind that can gobble up mountains of data and spit out text that sounds like it was written by a human. But here's the rub. As these models get more and more powerful and have to chew on longer and longer strings of information, the computational cost, goes through the roof.
Yeah, it can get pretty intense.
And that's where our deep dive today comes in. We're going to be looking at this new approach called Natively Trainable Sparse Attention, or NSA for short.
Catchy.
It is, yeah, and trust me, this thing is a game changer.
It really is. Long context models are becoming super important all over the place, from in-depth reasoning to generating complex code to having these super smooth conversations that flow over thousands of tokens, like you said. We've seen some pretty amazing breakthroughs lately with models like DeepSeek R1 and Gemini 1.5 Pro. They can handle crazy amounts of information.
It's wild.
Yeah, but the bottleneck, it always comes back to those traditional attention mechanisms. There are estimates out there that say they can eat up something like 70 to 80% of the total processing time just when you're decoding a 64,000 length context.
70 to 80%, that's like running a marathon with a piano on your back.
Yeah.
It's not ideal.
No wonder we need a better way to do things. So how does NSA lighten the load? What's all this dynamic hierarchical sparsity about?
Okay, so imagine you're a detective, you've got this huge case, and tons of evidence. Are you going to pour over every single tiny detail?
Probably not.
No way. You're going to zero in on the key clues, the stuff that's most likely to crack the case, right? And that's basically what NSA does. It uses dynamic hierarchical sparsity to find and prioritize the most important info in a huge sea of data. It makes the whole thing way faster and more efficient. Okay, that makes sense. But before we get into the nitty-gritty of how NSA works, can you give us a quick refresher on attention mechanisms in general? Like, why are they so important for language models? And why do they turn into such a computational nightmare when the input sequence gets super long?
Sure thing. So at their heart, attention mechanisms let a language model focus on the most important parts of the input when it's making predictions or generating text. Because like when you're reading a book, you don't memorize every single word. You pay attention to the key sentences and paragraphs, right? The ones that really drive the story forward. Attention mechanisms help the model do the same thing. But the problem with traditional attention is that it tries to analyze the relationships between every single word or token in the input sequence. And as that sequence gets longer, the number of possible relationships just explodes.
Combinatorial explosion.
Yeah.
You don't want to go there.
Exactly. And that's what leads to those crazy computational costs we were talking about.
Right? It's like trying to follow every single conversation in a room full of people. It just gets overwhelming. So NSA swoops in to create a more focused, streamlined approach.
You got it. Instead of wrestling with all those computationally expensive key-value pairs, NSA generates a smaller, smarter set that's tailored to the specific task you're working on. It's kind of like compressing a giant file. You're making it smaller without losing the crucial information.
Okay, I'm with you so far.
Equations 3, 4, and 5 in the paper get into the mathematical nitty-gritty, but the main takeaway is that NSA finds these really elegant ways to reduce the computational burden without sacrificing accuracy.
Cool. So let's unpack this dynamic hierarchical sparsity a little bit more. What strategies does NSA use to achieve this efficient representation of information?
Okay, so NSA has 3 main strategies. Each one plays a crucial role in striking that perfect balance between speed and accuracy. The first one is token compression. Imagine you have this super long document and you need to condense it into a short executive summary. That's what NSA does. It groups sequential blocks of keys and values together and creates these condensed representations that capture the essence of each block. It's like compressing a 100-page document into a 10-page overview. It makes finding the information you need so much faster. Equation 7 in the paper shows how this is represented mathematically.
So instead of analyzing every sentence, NSA is strategically grouping them to get the big picture right.
Exactly. But relying only on summaries can sometimes mean missing out on important details. So that's where the second strategy comes in. Token selection, NSA intelligently picks out and preserves the individual tokens that have the most important fine-grained information. It's like highlighting the key sentences in that executive summary. You don't miss those crucial points. Equations 8 through 12 in the paper lay out how the selection process works.
So it's a two-pronged approach. Compress for efficiency, but also hold on to those essential nuggets of information.
Right, and the third strategy is the sliding window. This mechanism makes sure NSA captures those local patterns and context without getting bogged down by information that's far away in the sequence. When you're reading a book, you focus on the page you're on and maybe a few pages before and after to keep things in context.
Hmm.
Right, you don't jump all over the place.
That'll be a pretty disorienting reading experience.
Laughs. Yeah, and the sliding window helps NSA stay focused and avoid getting distracted. Equation 12 in the paper has the technical details, but the important thing is that NSA does a really good job of balancing these three strategies, compression, selection, and sliding window, to process information super efficiently without losing sight of the big picture or those little details that matter.
It sounds like a well-rehearsed dance of efficiency. But this isn't all happening in some abstract theoretical world. We're talking about real hardware here.
Yeah.
So how is NSA implemented in a way that takes advantage of all the power of modern GPUs?
Oh, this is where it gets really interesting.
I love it when you say that. Give us the scoop on the hardware optimization magic.
All right, so NSA's implementation is all about squeezing the most performance out of modern GPUs, especially the ones with those powerful tensor cores. Think of it like organizing a warehouse for maximum efficiency. You wouldn't just scatter items randomly, you'd group similar things together in blocks that are easy to access. And that's similar to how NSA structures data for processing. It focuses on blockwise memory access and computation, which lines up perfectly with how modern GPUs are built. Figure 3 in the paper gives you a visual representation of this.
So it's all about streamlining the data flow, making sure the GPU can grab and process information as fast as possible. That makes sense. Now, the big question, does NSA actually deliver? How does it perform in practice?
The results are pretty impressive, to say the least. NSA has gone through rigorous testing, and it either keeps up with or even beats the performance of full attention models on a bunch of different benchmarks, including the ones that focus on long context tasks and complex reasoning. We'll dive into the specific results a bit later, but the bottom line is that NSA gives you some serious speed improvements, especially as the sequence length grows. And this advantage isn't just limited to one stage. It's across the board: decoding, forward processing, backward processing. It's not even just about speed in a lot of cases. NSA actually makes the performance better.
Wow, so it's faster and often better, too. That's
Right.
remarkable. But I'm curious to hear your thoughts. What really stands out to you about NSA? What is the potential implications of these findings? Let's take a second to think about those questions as we get ready to move on to the next part of our discussion.
What really blows my mind about NSA is that it's not just like a Band-Aid solution. It's a totally new way of thinking about how we handle attention in these big language models. The fact that you can train it from the ground up, it adapts to the specifics of whatever you're doing, and at the same time it gets these huge speed improvements. It just opens up so many possibilities for AI development in the future.
It's like we found a secret shortcut to a whole new level of AI awesomeness.
Yeah, exactly. And if you take a step back and look at the big picture, NSA could be the key to making even crazier, more groundbreaking AI applications possible. Imagine models that can process and reason through just mountains of data, whole libraries of books, gigantic code repositories, massive scientific databases. I mean, the possibilities are insane.
It's like giving these models superhuman powers of information absorption.
Right. But the paper also mentions that the researchers tried a bunch of other approaches while they were developing NSA. Can you tell us about those and why NSA came out on top?
Yeah, for sure.
So they started by trying to adapt some existing sparse attention methods to the training process, but they ran into some major roadblocks. For example, they looked at clustering-based strategies, but those added a ton of computational overhead, and they had trouble with optimization, especially when you're dealing with complex systems that use mixture of experts, or MOE.
So clustering sounded good in theory, but just wasn't practical in this situation.
Yeah, it's like trying to jam a square peg in a round hole. It just didn't work. They also tried out a bunch of different blockwise selection strategies, but those either relied on non-differentiable operations or these heuristic methods that just didn't perform as well. Overall, the paper shows that NSA consistently outperformed these other approaches. It had better loss curves during that crucial training phase. Figure 7 shows that really clearly.
So NSA was more robust and efficient during training. It basically beat out all the other contenders. But I'm curious, did the researchers learn anything about the nature of attention itself while they were working on NSA?
Oh, that's a great question. One of the most interesting things they found came from visualizing the attention map of a full attention model, shown in Figure 8 of the paper. They noticed that attention scores tend to cluster together in blocks, meaning tokens that are close to each other in the input sequence often have very similar attention scores. It's like there's this spatial relationship within attention patterns.
So tokens that are neighbors in this sequence tend to have the same level of importance to the model. That's pretty cool.
Yeah, and that observation was really important in shaping NSA's blockwise selection strategy by working with blocks of tokens instead of individual tokens. NSA can take advantage of that natural spatial relationship and be more efficient without sacrificing the accuracy of its attention.
It's like NSA is working smarter, not harder. It's using those patterns in the data to its advantage. The paper also mentions some other related work in sparse attention. Can you give us a quick rundown of the different approaches that people have tried?
Sure, researchers have been trying to optimize attention efficiency for a while now, and they've explored a ton of different techniques. One popular approach is to use a fixed sparse pattern, where the model only pays attention to a predetermined set of tokens. Methods like sliding window and streaming LLM fall into this category.
So those methods have like a set attention strategy that never changes no matter what the input is.
Exactly. Another approach is dynamic token pruning, where the model decides on the fly which tokens to keep and which to get rid of based on how important it thinks they are. H2O-BUZZ and SnapKV are good examples of this adaptive approach.
So those models are more flexible. They make decisions based on the specific context.
Right, and then you've got query-aware selection, which is where NSA really shines these methods. Things like Quest NFLLM and Cluster KV focus on picking the tokens that are most relevant to the specific query at hand.
So it's like each query gets its own personalized set of tokens, making sure the model is zeroed in on the most relevant information.
You got it. And as we've talked about, NSA takes that idea even further. It combines query-aware selection with token compression and that sliding window mechanism, and the result is a super efficient and powerful system.
It's like the ultimate attention optimization trifecta. Now the paper gets into the efficiency analysis of NSA, comparing it to those traditional full attention models.
They really put NSA through the ringer. They tested it on this powerful 8-GPU A100 system.
Whoa.
Yeah, some serious hardware. And they carefully compared its performance to full attention, looking at both training speed and decoding speed across different context lengths.
Okay, so let's start with training. How much faster was NSA?
Get ready to be blown away.
Yeah.
Figure 6 in the paper shows that NSA gets faster and faster as the context length increases. We're talking up to 9 times faster for forward processing and 6 times faster for backward processing. With a context length of 64,000 tokens, the longer the sequence, the bigger the advantage.
That's a huge improvement in efficiency. It's like going from a horse and buggy to a supersonic jet. But what about decoding? You know, the process of actually generating text token by token. That's where those memory bottlenecks can really cause problems, right?
Oh yeah, decoding is a memory hog because you have to access the whole key value cache, which can be gigantic. Table 4 in the paper shows the memory access volume for both NSA and full attention, so we can see how they stack up.
So does NSA slay the memory monster?
It does. NSA drastically reduces the amount of memory you need to access during decoding, and that leads to some serious speedups, up to 11.6 times faster with that same 64,000 context length. And just like with training, the longer the sequence, the bigger the speed difference.
So just to recap, NSA is faster at training, faster at decoding, and it either matches or beats the performance of traditional full attention models. Sounds like a total game changer for AI.
I couldn't agree more. NSA is really pushing the limits of what we can do with long context language models. It's paving the way for this whole new generation of AI applications that can handle more and more complex and data-heavy tasks.
It's so cool to see these breakthroughs happening. What does this mean for the future of sparse attention research? Where do we go from here?
Well, that's the big question. NSA has shown us what it can do, but the field of sparse attention is still evolving like crazy. The search for that perfect architecture, the one that gives us the best efficiency and performance, it's still going on. Researchers all over the world are coming up with new techniques, trying to find even better ways to represent and process information. Imagine models that can understand context lengths of millions of tokens, that can understand whole books, or these super complicated code bases in one go. That's the ultimate goal.
It's a goal worth shooting for, that's for sure.
Yeah.
This has been an incredible deep dive into the world of natively trainable sparse attention. I feel like I have a much better understanding of how these powerful language models actually work.
It's been great talking about this with you and all our listeners.
Before we sign off, any final thoughts for our audience?
I want everyone to really think about what NSA and innovations like it could mean for the future of AI. We're on the verge of a whole new era of intelligent systems, and breakthroughs like this are what's driving this amazing transformation. So stay curious, keep exploring. Who knows, maybe you'll be the one to make the next big discovery in AI.
That's a great note to end on. A huge thank you to our expert for walking us through this research paper, and to all our amazing listeners for joining us on this deep dive into natively trainable sparse attention. Until next time, keep learning, keep asking questions, and keep pushing the boundaries of what's possible.